So hello friends, welcome in the lecture of Geometrical Optics. So today we are going to discuss cardinal points in optical system. See, in previous lecture we studied equivalent focal length of coaxial system of two thin convex lenses. So instead of using a single convex lens, we saw the combination of two convex lens system, in which we saw if these are say L1 and L2 are two convex lenses, and we obtained a relation for equivalent focal length, so that equivalent focal length f is equal to f1 plus f2, these are focal length of lens 1 and lens 2, plus f1 plus f2 minus x. So x is distance between these two lenses original, and then if we use a lens of this focal length and if we place it at a particular position, now our question is that how to choose that particular position. Okay, and there comes into picture the cardinal points which we are going to study. We already saw the lens where we equivalent lens where we put, that is a principal plane or corresponding point is P2. So what those things are, that we are going to see today. Now question is, what are the points P, F and N? So these are the cardinal points which we are going to study. What exactly are they? So now here you already saw, here it is, a first lens has certain focal length, second lens also has certain focal length, and so on. So how it is associated with the system. Second, remember that principal point, focal point and N, nodal point, these are basically the cardinal points in optical system. So now important question is, why study of cardinal points is important in geometrical optics. So see, for that we'll think about some important concepts. See, we already know, if let us consider this is a boundary which separates two media, say this is a media having refractive index mu1 and this is another media, say let us consider glass, having refractive index mu2. So it is separated. So in this case, see, this is a plane surface. Note that it is not a curved surface. So normal to this plane is shown here, and whenever any ray of light incident on the plane, it makes that we know angle of incidence, that is I. Okay, and thereafter it refracts. Refraction is due to the property of refractive index of that particular material, and as refractive index of the material 1 is different than material 2, it refracts. Now important thing is that here we observe that instead of going straight, it is bent towards the normal. So it is happening when refractive index of the second material or second media is greater than the first one, then it bends towards, or we can say that in high refractive material it bends towards normal. So this is sin I. So obviously this is sin R, and that we already saw Snell's law, that is, sorry, here, there it is wrong, Snell's law, that is sin I upon sin R is equal to mu2 upon mu1. That is what the case is. Now here, before starting, we should understand few important concepts. See, if it is a plane surface, okay, and this is a normal, so if a ray refracts making an angle I, so at whatever point, if it makes the same angle as this is, it will refract with same angle. the angle of refraction will be same because of angle of incidence is same. Here it is. Now when we talk about the lens, surface is not plane. Remember that it is a curved surface. Okay, and when it is a curved surface, and let us consider this is the point optical center. So whenever a ray falls to this point, at this point you can see that the ray incident is completely normal, so it goes straight. But suppose the same parallel ray when incident at this point, so note that the normal to this point is now from line from, say, let us consider this is center of curvature. So here we get this is normal. So you can understand normal is in this direction, and so now as it was doing this kind of angle formation, but here the same parallel ray gives different angle of incidence. So obviously the angle of refraction will be different. So one important thing you note that the ray which is passing through optical center, and here in this case it is normal to the point or plane at that particular point, then it goes straight through optical center. That you should remember. Now here in optical instrument, generally 2 or more lens system is used to reduce the aberration in image. So remember, in case of single lens system, the main problem is that formation of image. See, whenever we consider that very thin lens, that is first thing. And second thing, when we talk about an object, though for formation of image diagram we show this angle very large, but basically the rays, actually those which are very parallel to the optical axis, only those are considered. But practically you can see that as we go away from optical center, the ray does not remain parallel, and so angle of incidence is very large, and that is why after refraction they do not meet at a single point, and that is why sharp image is not observed. Okay, so that is basically a problem with a single lens system, and that is why we get aberration, deviation in formation of image, and to reduce that we are using more lenses, 2 or more lens system. So here we already saw if this is an object, okay, and in case of 2 lens system the formation of image is taking place, so it is refracted by delta 1, due to second lens it is refracted by delta 2, and finally this is the point, okay, where the image formation takes place, that we already saw. Okay, now we again already saw that equivalent lens. So at that particular point H, so when it is retraced back, and let us consider if this lens is supposed to be absent, then by calculation we saw when ray reaches here, it must refract in this direction. So we put equivalent lens of equivalent focal length. So this is we already saw. Now important question is that what is the place of this equivalent lens from an object, so that you will get the image at the same point of the same size as we are getting using 2 lenses. So for these things the knowledge of cardinal point is very important. So here we see, if we consider a thick lens, and let us have shown here suppose thin lens. So whenever we talk about, so the main here in case of thin lens, actually we are considering that these 2 surfaces, this and this, they are so close to the optical center, so this distance is negligible, and we assume that optical centers and the poles are actually coinciding, and if this is an image, we measure all distances from optical center. Okay, that is what about thin lens, and we consider thin lens is very thin. But if we consider this kind of thick lens, then understand that when a ray incident on the first surface, okay, and now after that it refracts. So let us consider this is a first refraction which is making certain angle delta, and second time again instead of going straight it bends towards normal, so this is delta 2. So refraction is actually taking at 2 points, and now in this case it is difficult, in case of thick lens or multi-lens system, it is difficult to understand from where exactly we should measure the distance of object and distance of image. That is what the point, and so that is why we should think about the cardinal points. So same is the case with two optical systems, because of when a ray is incident on first lens it refracts the ray, but similarly second also refracts the ray. So whenever object formation is done, image formation is done, or object or focal length, so from where actually we should measure, from this or this, that is what the problem. So in 1841 Gauss proved that any coaxial system, that means see these are multi-lens system, but the lenses are arranged such that optical axis is same. So any coaxial system can be replaced by a single thin lens. Now here, instead of using two thin lenses, we can, using formula and calculations, we can have a single lens of a particular focal length, that is equivalent focal length, and can be placed at a particular point. So here you see that we already saw this thing. See here it is, we already saw that whenever first ray is refracted, when second refraction takes place, we extended the line in backward direction, and the line, that means ray QR and this ray intersect at this point, and the plane drawn through that point particularly, that is called as a principal plane. So that is why the lens is placed along HP2. So this lens formation can be applied. This lens formation can be applied with restriction that the image and objects are measured from two theoretical imaginary planes fixed with reference to the refracting system. So that is important. Now instead of using two lenses, when we place single lens, then question is where from the distance are measured. So for that, remember that this is important, that the image and objects are measured from two theoretical imaginary planes fixed with reference to that refracting system, and that we are going to consider. See, points of intersection of these planes with axis of an optical system are called as a principal points. So first principal point, which already we saw, that means when ray is refracted from first lens, then it bends towards this, and again it bends. So when the ray is traced back, the point of intersection gives us a point, and when a particular line is drawn intersecting the principal axis, that particular point is called as a principal point 2, and the plane passing through H and P2, that is called as a principal plane. So point of intersection of this plane with axis of an optical system are called principal points or Gauss points. So P1 and P2. So this is for the right hand side. Similarly we'll get for first lens also. So that is P1 and P2. So see, there are 6 points in all called cardinal points. So we already know there are 2 points, that is F1 and F2. These are focal points. Similarly we saw principal point 2. We are going to see another point, principal point 2. So the plane corresponding to these are called as the principal planes. They are passing through these particular points. And again, two more points are there. Those are called as a nodal points. See, with the help of these points, position and size of the image can be formed. Now we are going to see how it is exactly done. See focal points F1 and F2, principal points P1 and P2, and nodal points N1 and N2. See what is focal points. See, if we consider this is a lens L1. So we know that what is focal length, that when two rays or rays parallel to principal axis incident on the lens, then after refraction they meet at a particular point, and that is called as a focal point. So that is F2. See, when object is at infinity, rays are coming parallel to optical axis, and wherever they meet, that focal point is named as F2. See, when set of parallel rays to principal axis incident on convex lens and after refraction converge at a point, the point F2 is called second focal point. So this is second focal point. So in that case, remember that object U is at infinity and image is for the rays are intersecting at the point F2. So this is one of the cardinal point. Now here you see the object is placed at focal point. Then exactly what is happening? The rays incident on the lens, and if the object is at focal point, then the rays which are incident on the lens, they travel parallel to the principal axis. So important thing is that in first case what we saw, object was at infinity and rays were coming parallel and refracted rays were meeting at the point focal point. Here the rays are coming from focal point and after passing through lens they go parallel. So when rays starting from axial point, the point on axis is called as axial point, and after refraction become parallel to the principal axis, the point is called second focal point. So in this way, these are two cardinal points F1 and F2. So in this case, remember that object is infinity, rays are meeting at point F2, and here the object is at focal length. Okay, the image formation is at infinite distance because of the rays go parallel and parallel rays form image at infinity. Focal points F1 and F2, remember that, of the optical systems are defined as the pair of points on the principal axis of the system and conjugate to points at infinity. So what does exactly means? There it is a relation. That means if rays are coming from infinity, it will meet at focal point, and if rays are emerging out from focal point, they will reach to infinity. So this way these points are called as a conjugate points. So here coming from infinity parallel, meeting at F2, then emerging from F1 and going to infinity. So that is why these are called as a conjugate points. So now we are talking about principal points and principal plane. So for this, instead of using two lenses, now we are considering one thick lens. So this is a first surface of the lens and this is second surface of the lens. Now we have to find out principal points and lens. And remember that we already saw if the lens is thick, okay, so once the ray is incident on this, it refracts instead of going straight. Okay, second thing, once it reaches here, instead of going straight, it again refracts. Okay, and whenever we trace this line back, okay, so point of intersection is actually giving us the point H, and this is optical axis. If we draw a line and this line cuts the optical axis, and that is actually a principal point P2. Remember that. So same way here it is, you see the ray is coming parallel. Instead of going straight, it refracts and reaches this point. Okay, so later on again refraction is taking place due to secant surface. So instead of going straight, it refracts in this direction, and if we retrace this line back, you get the point. And if you draw a line through this point and optical axis, perpendicular to optical axis, you get the point P2, and this is called as a second principal plane, and this is a principal point. So far we saw cardinal points F1, F2. Now we got this principal point P2. Okay, and the plane passing through H2 P2, that is called as a second principal plane. Similarly, when ray is emerging from F1, when it reaches to first surface, so instead of going straight, actually it refracts. So from that it refracts, and once it refracts, it will reach to this point, and again at that point, instead of going straight, it will go parallel. So we know that ray emerging from focal point goes parallel, and when parallel ray incident on the lens, it passes through second focal point. So this is first focal point. Now the ray which is traced here, okay, and this is the line, otherwise it would have gone straight, that is a point H2, and the plane passing through it is called as a first principal plane. So this is a first principal point P1, and the plane passing through H1 P1 is called as a first principal plane. The planes H1 P1 and H2 P2 are pairs of conjugate planes such that, remember that, distance H1 P1 is exactly equal to H2 P2. H1 P1 is exactly equal to H2 P2. That is, the lateral magnification of the plane is 1. So whatever angle is traversed by this, the same angle will be traversed by this also. And P1 F1 is first principal focal length. Now see, here it is. Actually, whenever we talk about the lens, say this is a very thin lens. When we talk about thin lens, and whenever we measure focal length, suppose this is a focal point, so what we consider, instead of measuring here from, actually we are considering these are so close that focal length is measured from this point. Now here it is the case, remember that this is a lens, center is somewhere different, okay, but in case of this focal length, so when you need to measure the focal length, so see P1 F1, so from first principal point the length is measured up to F1, and this is a focal length F1. Similarly, the distance is measured from P2 to F2, that is a second principal focus, and these are that two imaginary lines from where we are actually measuring the distance of F1 and F2, object distance or image distance. So this is the concept of using cardinal points in solving the problems. Now let us consider the third pair of cardinal points, that is nodal points and its corresponding planes. So before understanding nodal points, remember one important thing, and that is very important to understand the cardinal nodal points. See, if this is a lens, that we know. If this is optical axis, first important thing that you know, the ray which is parallel, okay, it refracts and passes through focal point. That is first important thing, okay. Here when ray is parallel, it passes through focal point. Second important thing, when ray emerges from focal point, it goes parallel. That is important thing. Now third important thing is that the ray which is passing along optical axis passes through optical center, it does not deviate because of here the angle is 90 degree. Okay, but there it is one ray. Say suppose this is an object, and when a ray is passing through optical center, it also does not deviate. That is important thing to understand the concept of nodal points. That means the ray which is passing through the optical center, okay, but it is not making an angle of 90 degree with the normal at that point, but still it goes straight, and that is a basic concept needed for understanding the nodal points. So why this ray goes straight? The simple thing is that whatever curvature here, the same curvature, opposite curvature is here. Remember that if the ray would have been here and if it is refracted, then curvature at these 2 points are not exactly opposite, but here they are exactly opposite when it passes through optical center, and that is why there is no deviation. Whatever angle made due to refraction at this point, same and opposite angle is made at this point, and so that is why there is no deviation when ray is passing through optical axis. That is important thing. So that concept is important for nodal points. Now let us consider that H1, P1 are first and second principal plane that we saw. Now AF1 and BF2 are first and second focal plane. So here it is AF1 for and BF2 are first and second planes. Now see, suppose from this point, actually remember that this is a focal plane. Okay, so from focal plane the ray is traveling parallel. So obviously instead, actually it should go straight. Okay, but we know that in case of thick lens, bending is refraction is taking place from the principal plane. So here it refracts, and there it is another point in the lens through which actual refraction is taking place. So see, here it is, the refraction of the ray is in this way. Okay, and now the ray which is parallel, now remember that we are not talking of the surface of the lens. Okay, so these points are not on the surface. Actually these are the imaginary planes which we have studied by calculation. When it reaches, there it is a corresponding point on this line such that it gives the refraction. So that is what it is here. Now this ray is parallel to optical axis. Let us consider, we know that another ray, so this is a parallel and then it bends. This is what the situation we saw. This is from, it goes up to first principal plane, and from second principal plane it bends. Okay, similarly now let us consider this ray which is passing through optical center. Okay, so suppose that ray is deviating in this direction. Now that ray, remember that, does not refract, it go straight. So there must be a corresponding point on principal plane such that there will be a refraction, that the ray will emerge out but there will be no change in angle. So corresponding ray is coming out from this. So remember that these are parallel. That is important thing. So here it is a plane and here it is another principal plane, P1 and P2. So now when this ray intersect the optical axis, that point is called as a nodal point, which we are studying. Here, when the ray is emerging out from this plane or imaginary line, when it intersects optical axis, that is called as a second nodal point. So remember that angle made by this ray with optical axis is alpha, and this also alpha. That means there is no change in angle made, and that is why the ray goes straight. So remember that this and this having equal inclination, and the ray passes straight. So now these are the points where the ray A, let us consider this is N1, cuts the principal plane, and that is this point. Similarly, this is a point from, so they are such that distance P1 to this point and distance P2 to this point are same, and these points are nothing but T1 and T2. So here you see the point of intersection of incident ray A T1 and its conjugate ray T2C with principal axis are called as a nodal points. So what is nodal point? Now nodal points are defined as a pair of conjugate points on the axis having unit positive angular magnification. So whatever angle is made here, the same angle is made here, and the ray travels straight. So this pair is called as a nodal points N1 and N2. So nodal points and nodal planes that we already saw. Now from the figure which already saw, okay, so here we can see that in the figure triangle T1 P1 N1 and triangle see T1 P1 and N1 and triangle T2 P2 N2 are congruent, they are same. So obviously the distance P1 N1 is equal to P2 N2. So P1 N1 is equal to P2 N2. Now we are going to add this P1 N1 plus this distance. So it will become P1 plus P2. Similarly, we are going to add P1 N2 plus this distance. So that will become equal to this P1 P2. Obviously that will be N1 N2. So see, adding distance N1 P2 on both sides. So Pn N1 plus N1 P2 is equal to P2 N2 plus N1 P2. So from this C, P1 N1 plus N1 P2, P1 N1 plus N1 P2 is nothing but P1 P2. Similarly, when we talk about N1 P2 plus P2 N2, that is nothing but N1 N2. So from this we get P1 P2 is equal to N1 N2. Now here we have another triangle, that is triangle AF1 N1, that is AF1 N1, and H2 P2 F2, this is H2 P2 F2, they are also congruent, and from this we can say that distance F1 N1 is exactly equal to distance P2 F2. Okay, so remember that P2 F2, F2 is a focal point, this is a focal plane that we already saw. Okay, so P2 F2 is nothing but a focal length, don't forget. Okay, so now F1 N1 is equal to P2 F2, but F1 N1, if you talk F1 N1 is nothing but F1 P1 plus P1 N1. So here it is. Okay, but we already know F1 N1 is equal to P2 F2, and F1 N1 is also equal to this. So we can say that this P2 F2, putting the value of F1 N1 here it is F1 P1 plus P1 N1 is equal to P2 F2. Or from this we can say that is P1 N1, this is equal to P2 F2 minus this F1 P1. Okay, but I already told you that P2 F2 is nothing but P2 to F2. Remember that focal length is measured from principal point 2. So P2 F2 is nothing but focal length F2, and similarly P1 F1 is nothing but the focal length, that is equal to minus F1. We already know that to right of the optical center the length is measured positive and to left it is negative. So here now we can see that this is F2, this is F1. So putting, we get P1 N1 is equal to F1 plus F2. So here we saw P1 N1 is equal to F1 plus F2. But see, we know already that P1 N1 is equal to P2 N2. That we already saw. So here, therefore, here it is P1 N1 is equal to P2 N2 is equal to F1 plus F2. That we get. And if medium on both sides of the lens are same, then we have F is equal to minus F. So that is why this term becomes 0, and we get P1 N1 is equal to P2 N2, that is equal to 0. And this is possible only when medium on both sides are same. And in that case, obviously from this relation, P1 N1 and P2 N2 is equal to 0. So obviously the nodal points coincide with principal points. This is what the concept of cardinal points, and they are very important for solving the problems of complex system. Okay, thank you very much. Bye.